the knowledge of quantum mechanics, combined with Einstein's theories of relativity, has shaped the modern world. For decades, Einstein's work has been central to our understanding of time, space, and the universe itself. His groundbreaking equations explained how gravity warps spacetime, how light bends near massive objects, and how time slows in strong gravitational fields. These theories have stood the test of time and are among the greatest achievements in science. However, recent discoveries in quantum computing are now challenging some of Einstein's beliefs about the nature of reality. Einstein was uneasy with the randomness of quantum mechanics, famously stating, "God does not play dice with the universe." He believed in a deterministic universe where everything followed predictable rules. Quantum mechanics, on the other hand, introduced ideas of uncertainty, randomness, and behavior that defies classical logic. The advent of quantum computers, which operate on the principles of quantum mechanics, has enabled scientists to test these ideas more deeply. In a recent experiment, researchers used a quantum computer to simulate space-time. The results were astonishing. Entangled particles appeared to communicate instantly over large distances, and their interaction seemed to reshape space-time itself, creating ripples in the universe. This suggests that space-time may not be static but could emerge from quantum processes. Einstein was skeptical about quantum entanglement, which he called spooky action at a distance. He believed it violated the principle of locality, the idea that nothing can influence something else faster than the speed of light. He argued that hidden variables, unknown factors, might explain this phenomenon. Over time, experiments known as Bell tests have shown that quantum mechanics, not hidden variables, correctly describes reality. Quantum computers process information differently from classical computers. While classical computers use bits, zeros and ones, quantum computers use qubits, which can exist in multiple states simultaneously. This allows them to perform calculations and simulations that classical computers cannot, making them powerful tools for exploring the quantum world. In the recent experiment, scientists observed entangled particles influencing spacetime in unexpected ways. This discovery suggests that gravity and spacetime might be quantum phenomena. If true, this would align with theories like loop quantum gravity and string theory, which propose that spacetime is made of tiny, discrete building blocks. It also raises profound questions. If spacetime emerges from quantum processes, what lies beyond it? Could there be a deeper layer of reality that gives rise to the quantum world? This discovery also touches on the role of observation in quantum mechanics. The observer effect suggests that reality is not fixed until it is measured. This raises the possibility that our observations might influence not just quantum systems but also the structure of spacetime. Some scientists even speculate that consciousness itself might be a quantum phenomenon, deeply connected to the fabric of the universe. Quantum computing has practical applications beyond theoretical physics. It has the potential to revolutionize fields like cryptography, artificial intelligence, and material science. However, this technology also comes with ethical concerns. Quantum computers could make current encryption methods obsolete, raising cybersecurity issues. Manipulating quantum systems could also have unforeseen consequences. This new quantum era challenges Einstein's deterministic worldview but doesn't diminish his legacy. Instead, it builds on his work, pushing the boundaries of our understanding. Quantum discoveries remind us of the complexity and beauty of the cosmos. They force us to rethink fundamental concepts like time, causality, and even existence itself. In the quantum world, time may not exist as we understand it. Events can happen out of order or even simultaneously, a concept known as quantum causality. This challenges our traditional ideas of cause and effect. Some scientists believe that time, like spacetime, is an emergent property of quantum interactions. If true, it means our perception of past, present, and future might be an illusion. There is also growing evidence that spacetime might not be continuous, but instead composed of tiny, indivisible units called Planck lengths. Quantum computers, operating at these scales, could one day simulate the universe itself, giving us insight into how spacetime emerges from quantum processes. Some researchers propose that the universe might be a hologram, a three-dimensional projection of information stored on a two-dimensional surface. Quantum experiments have found patterns in entangled particles that support this idea, suggesting that our reality might be a shadow of a deeper, more fundamental one. This raises philosophical questions. If the universe is a hologram, what is projecting it? Could we ever understand or interact with the mechanism behind it? These discoveries highlight the profound mysteries of the universe. While Einstein's theories laid the groundwork, quantum mechanics and computing are taking us further, revealing a reality that is both stranger and more fascinating than we could have imagined. The quest to understand the universe continues, driven by curiosity and the desire to unlock its deepest secrets. The world we observe might actually be the result of computational processes happening in higher dimensions. In this perspective, the universe itself could be seen as a kind of quantum computer, processing information on a scale far beyond what humans can understand. If this sounds like science fiction, consider the field of digital physics. Digital physics is a branch of theoretical physics that suggests the universe functions like a massive, complex computational system. In this view, everything in the universe, atoms, particles, galaxies, can be thought of as bits of information, similar to the ones and zeros used in classical computers. Quantum computers, which process information in unique states, like superpositions, give us a glimpse into how such a computational universe might operate. In fact, some scientists believe these advanced computers could one day test the digital physics hypothesis and show that the universe is, at its core, a system of information processing. But if the universe is a quantum computer, what does that mean for us? Are we just programs running in this cosmic system, or do we play some unique role in shaping reality? These questions lead us to one of the most fascinating aspects of quantum mechanics, the relationship between consciousness and the quantum world. Quantum mechanics has something called the observer effect, where the act of measurement seems to influence the outcome of a quantum system. But what counts as an observer? Is it only humans, or could any interaction with the environment qualify? And if human consciousness does have a special role in shaping quantum reality, what does that tell us about the mind? Some scientists, like Roger Penrose, believe that consciousness might itself be a quantum phenomenon. Penrose's theory, called orchestrated objective reduction, OR, suggests that tiny structures in brain cells, known as microtubules, operate at the quantum level. According to this theory, consciousness emerges from these quantum processes. If Penrose is correct, it would mean our thoughts and perceptions are deeply connected to the quantum fabric of the universe. This idea has major implications for free will, creativity, and the nature of existence. For example, if our minds are quantum systems, then our decisions might not be entirely predetermined, they could follow the same probabilistic rules that apply to quantum particles. In other words, free will might be a fundamental part of the universe, not just an illusion. This raises even more intriguing questions. If consciousness is a quantum phenomenon, could it be simulated or recreated using quantum computers? Some researchers think advanced quantum computers could one day create artificial intelligence systems with consciousness-like qualities. Such advancements would force us to address ethical questions about life, identity, and the rights of these artificial beings. The idea of consciousness as a quantum phenomenon also opens the door to questions about life after death. If consciousness is rooted in quantum processes, could some part of it continue after the body dies? Though this remains highly speculative, it has sparked philosophical and spiritual debates. For instance, some researchers wonder if near-death experiences, where people report visions of light or feelings of interconnectedness, might be linked to quantum processes in the brain. As we continue exploring the quantum world, we're uncovering a reality that challenges everything we thought we knew about time, space, and existence itself. Quantum computers are not just tools for solving problems, they are revealing the fundamental building blocks of reality. But with such powerful discoveries come risks. Quantum computers allow us to simulate phenomena at incredibly small scales, such as the Planck scale, where space and time might not be smooth and continuous, but instead broken into tiny, discrete units, like pixels in a video game. Some researchers have even found patterns in the laws of physics that resemble error-correcting codes used in digital systems. This has led to the controversial idea that our universe might be a simulation. Physicist James Gates has pointed out that certain equations in physics contain embedded code similar to those used in web browsers. If this is true, and the universe operates as a simulation, then who or what is running it? And why? Quantum entanglement, a phenomenon where particles remain connected and instantly share information no matter how far apart they are, challenges our understanding of space and time. Some theorists suggest the universe might function as a multidimensional quantum network, where our three-dimensional world is just one layer of a much larger reality. If quantum computers can crack the code of reality, what happens if they reach the limits of the simulation itself? Would the program running the universe crash, reset, or behave in some unpredictable way? Prominent scientists like Michio Kaku and Neil deGrasse Tyson have discussed the simulation hypothesis as a legitimate topic. Tyson even speculated that the chances we're living in the space realities might be 1 in a billion. Kaku has suggested that future civilizations could use quantum computers to create simulated universes indistinguishable from our own. If we are living in a simulation, does that make our existence less meaningful? Or does it mean our actions have greater significance, serving a purpose we cannot yet understand? If undeniable evidence of the simulation were discovered, would society respond with enlightenment or chaos? Quantum computing has also reignited debates about the role of consciousness in shaping reality. The observer effect suggests that consciousness might influence the physical world in profound ways. Some experiments with quantum computers have shown systems choosing states based on the presence of an observer. This hints that the mind could be deeply connected to the universe's structure, acting as a bridge between the quantum and classical worlds. If consciousness is truly a quantum phenomenon, it could exist beyond the brain, potentially persisting after death. This idea, while speculative, inspires both scientific and philosophical exploration. As we push the boundaries of quantum research, we must also address the ethical challenges it brings. Advanced quantum technologies could transform medicine, cryptography, and artificial intelligence. But they also raise questions about power, responsibility, and the potential consequences of tampering with the fabric of reality itself. Quantum computers force us to confront profound mysteries, not just about science, but about the nature of existence. They reveal a universe that is dynamic and interconnected, where we, as conscious beings, are active participants. The discoveries we make in the quantum realm today will shape humanity's future in unimaginable ways. As we explore these uncharted territories, we must do so with curiosity, humility, and respect for the unknown.